In this video on section 7.1, we're going to talk about biased and unbiased estimators, and we're going to look at how the sample size affects the variability of a statistic. So first, in the book, page 430 describes what's called an unbiased estimator and a biased estimator. And when you're trying to estimate a population parameter, because you can't go around and actually figure out what the population parameter is, you take a sample multiple times, and you create what's called a sampling distribution. Now, in this example, Mrs. Washington's class actually went around, they found all of their heights, and they found a population mean, mu, and they found a population range as well. So they found the mean of all the heights in the entire class, that's your population mean, and they found the population range by doing the tallest kid minus the shortest kid. And then they started sampling of size 4. So they took repeated samples of size 4, and they found the mean of each sample, or x bar, and they graphed it. So here's the sampling distribution of the mean of each sample. You'll notice that all these x bars, they kind of center around 65, 66, 64, somewhere in there. The population mean is actually 66.07. The mean of the sampling distribution is 65.67. Those numbers are very close. And when those numbers match up, that means you have an unbiased estimator on your hands. So a sample mean, if you find the mean of that sampling distribution and it's equal to the population parameter, that means that estimator is unbiased. So instead of having to use all the time, resources, money to talk to every single thing, object, or person in the population, you can do a sampling distribution and infer what the population mean is from the mean of the sampling distribution. It makes it a lot easier than talking to everybody in the population. Now, this classroom is a very small population, so it's easy to find, but if you were to try and think about the population of the state of Michigan, millions of people, or even the population of the United States, over 300 million people to talk to, that might be way too much for you have time or money for. So you take samples, and you find a population, or you find the population parameter by estimating the mean of the sample distribution. So these two numbers are very close, so we call it an unbiased estimator, which is a good estimator for the population parameter. The second one is the sampling distribution for ranges. So while they were sampling, they did two things. They found the sample mean over here, and they put it on the distribution, and they also found the sample range and put it on this distribution. So it's the same samples, but they found the ranges as well as the means, and they graphed all the ranges for all the samples. You'll notice that the mean of this distribution is 10.12. So the mean of the sampling distribution is right about there. The problem is that the population range is actually 21 inches. These numbers aren't close. And when these numbers aren't close, you have what's called a biased estimator on your hands. The math's not going to work out so that you can use the mean of this distribution to find the population parameter. So if I wanted to find the population range, I couldn't use the sampling distribution of the sample range. It's not going to work. My number is going to be far off. If I wanted to find the mean of the population, I could use the sample means distribution and find the mean of that. That's an unbiased estimator. This, however, is a biased estimator. So we prefer to use unbiased estimators when we're trying to evaluate what a parameter is instead of a biased estimator. So our definitions are as follows. An unbiased estimator is a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter. So essentially, the center or the mean of the sampling distribution, if it's an unbiased estimator, we can call that the parameter without actually talking to everyone in the population. A biased estimator is the mean of the statistics distribution isn't equal to the parameter. And we talked about with the range. The range didn't match up with the population range. So we couldn't use that to estimate the population range. All right. Describing the relationship between sample size and the variability of a statistic. In Survivor, the TV example here, we have an assumption that the population proportion of people who watch Survivor on a weekly basis is P equals 0.37. The ratings companies don't necessarily know that the population proportion is 0.37. They haven't actually talked to everybody in the nation. But they will try to estimate it with samples. Below is a diagram with two sampling distributions of people watching TV, and P hat being the sample proportion that watch Survivor. Both have graphs of 400 samples within them. Compare the two graphs. So, we have two sampling distributions. Both of them have 400 samples within them, and both we took the sample proportion of people who actually watched Survivor. Now the first one, n equals 100, which means the sample size is only 100 people. So each one of these dots represents 100 people. This one has a sample size of 1,000, meaning that each one of these dots is 1,000 people. They still repeated the sample size 400 times in both, but the graphs of the distribution are very different because of the sample size. So in both of these, the center appears to be around 0.37. Okay, that lines up in both of these, which is a good thing. What's different though is the spread. The spread is different in the n equals 1,000 distribution versus the n equals 100. There's a lower variability in this bottom distribution than the top. There's a huge range of possibilities here, while there's not a huge range here. And when you have this, you're more precise with your measurements. So if you want a lower variability, simply increase the sample size. And that's your relationship. A lower variability comes from a higher sample size. So if you have a distribution where it's too far spread apart and you want to increase the precision, you simply increase the sample size. So if you want to get the most accurate proportion of people who watch Survivor, would you choose samples n equals 100 or n equals 1,000? We're going to choose n equals 1,000 because there's less variability. Our true population proportion can be more likely in the center here than maybe if it's further out in this spread of distribution here. So the variability of a statistic is described by the spread of its sampling distribution. So looking at a sampling distribution, how far is it spread out? That's your variability. It's mainly determined by size of the sample. We just talked about that on the previous page. Increase the sample size, you get a smaller variability. Now it says mainly because it's not entirely determined by size of the sample. Other factors actually affect it as well. Large samples give smaller spreads, just a general rule of thumb. And lastly, spread of sampling distribution does not depend much on the size of the population, as long as it is 10 times larger than the sample. If you have a sample that's more than 10% of the population, you run into an issue where the samples are going to be more alike than they are not alike, because you're sampling too much of the population. So it's not going to affect your p-hat value, but it will affect the variability of it. So the spread and distribution of your sampling distribution will be affected if your sampling is too big. So always make sure it's less than 10% of the population. Last thing about sampling. You have two things that affect, or things you want to look at for your sampling: bias and variability. So the ideal would be having low bias or no bias and low variability. You want a nice tight shot and be accurate with your measurement. You could also have high variability but low bias, which is still preferred. If you wanted to make this more like the bottom one, part D here, you would simply increase the sample size. These two have a high bias, which means we've missed the mark or the accurate measurement. Something went wrong with our sampling methods. Maybe we weren't doing the correct SRSs. Maybe we weren't sampling in the correct methods. That's where bias comes in. You cannot decrease bias by increasing the sample size. You can only decrease variability. So from here to here, all these people did, they changed from part C to part A, all they did was increase the sample size. They didn't get rid of the bias. Okay? Getting rid of the bias is just as important. You may have to look at your sampling methods in order to do that.